Welcome to Lecture 2.2b. Yesterday we talked about limits involving infinity. In particular, we talked about limits where x was approaching positive or negative infinity. And we saw that usually when that's the case, we end up with something called a horizontal asymptote. Well, today we're going to pick up continuing to talk about limits in infinity, but instead of limits as x approaches infinity, we're going to talk about limits that equal infinity. Now, take a moment, pause the video, and copy down this notation. You're used to me giving you the big idea, but I think by now you might be able to do that for yourself, and that's something that deserves a comment in the left-hand column. Great, so you hopefully were able to articulate for yourself that what this limit means is as x gets really close to some number c, the y value of the function is getting really, really large. That's what it means to equal infinity. Now, notice we're lying a little bit. It's not like you ever get infinity as a numerical answer. It's an idea. Similarly, we could say as x approaches some number c, f of x equals negative infinity, and what we mean by that is that really just f of x is getting very negative, so very small or a large number with a negative in front. In order to really understand this idea, we usually look at it in two different ways. We look at it numerically and graphically. I'm going to use this example to show you what these two concepts look like. Remember, though, that the answer to this example isn't really as important as the idea of, do you recognize it when you see it? So we're going to be looking at the limit as x approaches 2 of x over x minus 2. Normally, if we want to get a sense for what the numbers are doing, we would go to y1, and we would type in the equation here. Then we'd make sure that our table set has the independent variable asking u and the dependent variable calculating automatically. I've skipped this step, and I actually have a picture of what the table is going to look like, but you could probably recreate this on your own. So numerically, if I take this limit, which was, again, the limit of x over x minus 2, if I plug in values that are decimals that approach 2 from the left-hand side, in other words, these numbers are smaller than 2 and they're getting closer and closer and closer, what I observe is that the y values seem to be getting incredibly negative. Similarly, if I go past 2 and I look at numbers that are getting close to 2, closer and closer and closer, but these numbers are all larger than 2, the y values as I get closer and closer to 2 seem to be getting really large and really positive. So what we would say is we would say that the limit of x approaching 2 of x over x minus 2 from the left is negative infinity. And the limit from the right is positive infinity. Basically what that means is the actual limit doesn't exist. So when you write limit as x approaches 2 of x over x minus 2, this is the normal limit, and this would be does not exist. However, the one-sided limit does exist, and we could talk about the one-sided limit if we wanted to. We could say the limit as x approaches 2 from the positive side, and I'm just going to write f of x because you know what the function is. Well, and if we just want to talk about the positive side, I would say the y values, when I'm coming from the right, seem to be getting really, really large. And that would indicate that from the right, the y values are going to equal infinity. From the left, the limit as x approaches 2 from the left-hand side, the y values in my table got very, very negative. So I would say the limit equals negative infinity. We could also get these results looking at the graph. Using the graph, you'll notice this is just a normal rational function. It's got a vertical asymptote, and this vertical asymptote is at positive 2. If I try to approach positive 2 from the right-hand side, I trace my function and I observe what's happening to the y values. Well, the closer I get to 2, the more the y values increase. And in fact, they keep increasing forever and never really get to 2. That's why we have positive infinity for the right-hand side limit. The left-hand side limit, if I come from the left and observe what happens to the y values get lower and lower and lower and lower, and they continue going forever. And that's exactly what we mean by the left-hand limit equals negative infinity. Numerically, there's kind of a key idea here that you can start to use for your instinct. Anytime you have an equation that's going to end up with a positive number divided by a very small positive number. So for example, if I plug these numbers in, the bottom of this fraction becomes a really small decimal. Well, when you have that situation, a number divided by a tiny little decimal, the answer is usually going to be positive infinity. Now, if that small decimal is a negative number, any number divided by an infinitely small negative number, that's going to be negative infinity. And we're going to use these instincts to help us kind of estimate or guess some examples. Cool, so to recap, numerically, a limit approaches infinity if the y values get really, really high and positive or really, really low and negative. Graphically, what we see is the y values going up to the top or way down to the bottom of the graph. Using that idea, see if you can evaluate each of these limits. When we come back together, I'll show you how I would have done it. Great, so here's how I would think about these. This first limit, I probably would have put into my graphing calculator. And using the table, you should have seen that as we approach 0 from the positive side, 1 over x goes to infinity. The y value explodes. Now, another way to think about this is if you think about plugging in very small positive decimals, we would have 1 over a small positive number. And that's kind of the key for positive infinity. We've got a fixed number divided by a tiny decimal that's positive. You could have also seen this from the graph. The graph of 1 over x looks like this. As I approach 0 from the positive side, the y values go all the way up to the top. Any of these three methods works. Make sure that you understand the difference between them. Similarly, for the second one, maybe you put this into your graphing calculator. If you did, you should have seen that as we approach 3 from the left-hand side, this value is going to go to negative infinity. One way to see that is that approaching 3 from the left-hand side is like plugging in maybe 2.9. It's a number that's slightly smaller. And if I plug in 2.9 on the top, I get a positive number divided by a negative decimal because the number x is a little bit smaller than 3. So it's a negative decimal that's really small. And that number that's fixed divided by a tiny negative number is what causes it to go to infinity. Now, the last one is a little different. In fact, if you put this into your graphing calculator, you may not have been totally convinced. Here's what mine looked like. Since we're approaching 4 from the positive side, I chose numbers that were slightly larger than 4, and I put the function into y1, and this is what I got out. Now, what I notice is the closer we get to 4, the numbers are getting larger. However, they don't seem to be really going all the way to infinity. In fact, at 4, it kind of looks like there's a number. And this is where you can't exactly trust your calculator. For example, this isn't really at 4. It's actually a decimal that's really close to 4. And since I'm not convinced, you're going to need another strategy to rely on. So think about what the graph of ln looks like. You may remember that the normal natural logarithm graph looks like this. It crosses the x-axis at 1, and it has an asymptote at x equals 0. Well, if I subtract 4, basically what I'm doing is I'm shifting the graph to the right 4 times. So maybe I would get a graph that looks like this. 1, 2, 3, 4. That's the asymptote. And now the graph looks like this. Think about what it would mean to approach 4 from the right-hand side. Well, as I trace the graph, my y values are getting lower and lower and lower and lower. So actually, this one approaches negative infinity. And notice that we can't use our instincts, and we can't necessarily use the table, so you're going to need to be willing to try a couple different strategies. Now, luckily, I'm about to make that a lot easier for you. It turns out, what you may have already realized, is that every time we have a limit that equals positive or negative infinity, we're actually talking about a vertical asymptote. Your textbook has the definition, and you should copy down the definition, pause the video to make sure you understand the idea behind this. Great, so in addition to this definition, I'm going to talk about 3 examples. And the 3 examples are f of x equals 1 over x, and ln of x and tan of x. These are three functions that we know have vertical asymptotes, and just like we had some limits to memorize for limits as x approaches infinity, these are great limits to memorize because you can then use them to evaluate other limits. So think about this first function, f of x equals 1 over x. You should recognize what the graph looks like this. And we actually also just worked out an example like this. So this has a vertical asymptote at x equals 0. What that means in terms of the limit is that the limit as x approaches 0 from the positive side of 1 over x equals positive infinity. And that's because coming from the right, the y values go up to infinity. And we can also say that the limit as x approaches 0 from the negative side of 1 over x, that equals negative infinity. And that's because coming from the left, going towards 0 on the x-axis, the y values decrease. These you can take as given limits now, and we're going to use them and apply them to other examples. Similarly, the natural logarithm function is another function that we know to have a vertical asymptote. And that means there must be a limit equaling infinity or negative infinity involved. Here's the natural logarithm function. Looks like that. The vertical asymptote is again at x equals 0. And this time, however, we don't have both limits. In this case, it's only possible to approach 0 from the right-hand side. When we do that, when we approach it from the positive side, the y value of this function approaches negative infinity. If I wanted to try to evaluate the limit as x approaches 0 from the negative side, I would come to the other side of the graph, but what I realized pretty quickly is there's no function here. So this left-hand side limit does not exist. Only the right-hand side limit exists, and it does equal negative infinity. The last one that you should be familiar with is tangent. And remember that tangent is the same thing as sine over cosine. And so basically, anytime cosine equals 0, it's going to have a vertical asymptote. There are a lot of them. In particular, let's take pi over 2 as an example. Cosine of pi over 2 is 0. When you think about the graph of tangent, the shape looks like this. And then there's an asymptote at pi over 2, and then the shape repeats. So let's think about the left and the right-hand side limits. Well, the limit as x approaches pi over 2 from the positive side. I would be tracing this graph, getting closer and closer and closer to pi over 2, and you see the y values are approaching negative infinity. They get very, very low. If I try to approach this same x value, pi over 2, from the left, as I trace the function, the y values get higher and higher and higher. So we can say the limit as x approaches pi over 2 from the left of tangent equals positive infinity. Okay. Make sure that you have these 4 limits marked clearly in your notes so that you can use them for reference points later. Let's do some examples.